Hello everyone, and welcome to this course on computational modeling. My name is Ion Petre and I am with Obo Academy University and Turku Center for Computer Science. Whenever I talk about introducing modeling, I like to start with this metaphor of the blind man and the elephant. It's a legend widespread throughout many countries in Asia. It tells about 6 blind men feeling an elephant and each forming an impression of what an elephant is based on what part of the elephant they touch. The first man feeling the side of the elephant would say, an elephant is like a wall. The second man feeling the tusk of the elephant, he would say, an elephant is like a spear. The third one feeling the trunk might say, an elephant is in fact like a snake. The fourth one, feeling the knee of the elephant, would say, no, it's like a tree. The fifth one, feeling the ear, would say, an elephant is just like a fan. And the sixth one, who might feel the tail, would say, an elephant is just like a rope. This is a lot like building a model. We are given some data, often incomplete and with errors in it, and we aim to build a description of the reality based on that data set. The model we come up with is of course just a partial description of the reality, and its precise purpose is to describe the available data and to give some predictions about some of the properties or behavior of the object or phenomenon we study. So, a model is an abstract view of the reality and a representation of what we think are the main features of the reality. Obviously, for any given object of study, many models may be formulated, possibly focusing on different features of the object, just like the blind man and the elephant. It's important to understand also what a model is not. A model is not the reality. It's just a simplified representation of the reality that serves a limited and precise purpose, like identifying some properties of that reality. Also, a model is not certain. The world of modeling is one where a model can almost never be proven correct. A good model can be shown to fit the known data well, but there always remains the possibility that new data sets may render the model wrong. There is a huge momentum for modeling right now. The Human Brain Project and the Brain Activity Map Project are two major multi-billion research initiatives involving the goal of modeling the human brain. There is a lot of discussion around climate change models, also about economic forecast models, and in particular, bank stress models. Here are some simple but diverse examples of models. A building has many models: its foundation plan, water pipe plan, electricity plan, ventilation, room division plan. All of them are different models of the same building. One may also have philosophical models, political models, societal models, and so on. Here is another type of model, often called a Fermi approximation. How would one answer a question such as, how many piano tuners are in Chicago, having access to only generic data about Chicago and about the popularity of pianos in general in the society? One can reason and build a mental model as follows. So, Chicago has about 5 million people, and in average in the US there are about 2 persons in a household. So that means about 2.5 million households in Chicago. So let's say that we have some statistical knowledge that about 1 household in 20 has a piano, that it's used and needs regular tuning, and that only 1 tuning per year is enough. So this gives us about 125,000 tunings per year that need to be performed. So the number of piano tuners should be indicated by this need. More piano tuners than needed would lead to some of them going bankrupt because of lack of enough work. And less tuners than needed would lead to work left undone, and so eventually to more of them opening shop in the city. A piano tuner needs about 2 hours to tune a piano, including driving. So this gives us about 250,000 hours of work that need to be performed. If a tuner works 8 hours per day, 5 days a week, 50 weeks per year, this gives us about 2,000 hours of work per person. So this simple model predicts that there should be about 125 piano tuners in Chicago. To come up with this prediction, we used some statistical data and some simple economic models about demand and availability. In this course, we will focus on computational models. We will also call them mathematical models without worrying too much about the possible semantical differences between the two. So we will focus on models describing the reality through some sort of mathematical representation. The goal of the course is to give an introduction to the process of mathematical modeling. I will show you a number of techniques for building, analyzing, and utilizing a model. This is not a course in mathematics, but rather on the use of some mathematical techniques for the purpose of modeling. In general, I will show you quite little on the mathematical background of the techniques I discuss, and rather focus on how to use them in modeling. There are many advantages that a mathematical model may bring. A mathematical model allows for a precise formulation of the chosen aspects of the reality, and so that means that you have to formulate your ideas precisely, and you will have less implicit assumptions. It also allows for a precise formulation of the current knowledge of the reality, and so that brings you models as representations of knowledge. It also allows for precise reasoning about the reality. Based on the concise language, models can be analyzed in a formal way. It allows also for some type of analysis that would be impossible to perform on the reality. There is a large body of mathematical tools available, and so we can do things such as model checking, meaning verifying all possible behaviors of the model in time. We can do some scenario analysis, meaning that we can verify the behavior of the model in some well-defined extreme scenarios, for example, disaster scenarios. It also allows for predictions based on computational simulations. When building a model, it's important how to choose the variables, as it's equally important to decide what not to include in the model. If the wrong things are neglected, then the model is no good because you are missing some important parts of what should be modeled. Too much included, and you will have a hopelessly complex model that will have difficulties to say anything useful about the reality. Choose the internal variables wrongly, and the model will not capture its target. There is also the question of how general the model should be. If you want to model a table, for example, should it be any table, or should it be the specific table in front of the modeler? We will discuss in the course quite a diversity of modeling approaches. Some are based on continuous mathematics, others based on discrete mathematics. Some models we will build will be deterministic, meaning that their future is uniquely determined by their present state, while others will be stochastic, where many possible future evolutions are possible. Only elementary techniques will be discussed in this course. We will try to introduce the necessary mathematical background wherever we feel that our discussion will go beyond, say, high school mathematics. Here is a list of the topics we will cover in this course. We will discuss about modeling change, modeling proportionality and geometric similarity, model fitting, data-driven modeling, simulation-based modeling, discrete probabilistic modeling, discrete optimization modeling, modeling with ordinary differential equations, continuous optimization modeling. And the course book we follow in this course is a first course in mathematical modeling by Giordano, Weir, and Fox.